All right, guys, before we move on to the math instructions, we should really take a look at the different types of data types that are available within TIA and basically within any PLC. So the way that the TIA or Siemens sets their stuff up is in terms of bytes. So you may find differences between the types of data types, not the types, but the makeup of data types between like Siemens products and Allen Bradley products. But in terms of Siemens TIA, everything is in terms of how many bytes are within that, that word or that double word or that integer. So let's take a look at the different types here, guys. So we got basically four different types in that we have bits, bytes, words, and double words. And then we'll start talking about integers and the different types of integers as well. Okay, I've got separate pages on each of these guys, but essentially a bit is just a 1 or a 0. A byte is going to be made up of 8 bits. A word is going to be made up of 16 bits. And then a double word is going to be made up of 32 bits. So you can see that as we go through these different data types, obviously we have more and more information that can be held there. Okay, and you'll find that like in your tag table, if you give a tag here, like our start push button, that's a bool value. And so an example that would be %m0.0. If we have just a standard value, that might be a byte, right? That would be 8 bits. So the address for that would be %mb1. And then as we move up to words and then double words, then the addresses are %mw for word and then %md for double word there. When you look at the maximum combinations for each of these guys that we're talking about, then it would be basically 2 to the power of whatever the number of bits are there, right? So obviously if we have 2 to the power of 1, then there's 2 combinations for a bit, right? Either a 0 or a 1. Okay, when we look at the other ones, it'll be 2 to the power of 8, 2 to the power of 16, or 2 to the power of 32 in order to find out the maximum number of combinations that you can have. And then the maximum number is 2 to the n minus 1. And the reason why it's minus 1 is because everything in PLC logic starts with a 0. Right? So we're not starting at 1, we're starting at a 0. So if we have 256 different combinations, then the number is going to be between 0 and 255. Okay, we'll keep referencing back to this diagram right here, right? Essentially, we have a bit being %input 0.0. Then we have a byte. The byte would be 8 bits of information. Then if we have 2 bytes, that makes up a word, right? That's going to be 16 bits of information. And then if we have 1, 2, 3, 4 bytes, right? Remember I was saying that Siemens organizes everything in terms of bytes. So if you have 4 bytes, that would be 2 words, and that would obviously be a double word consisting of 32 bits. Okay, so I find this diagram really helped me out to organize my thoughts as to where different instructions are and where like a certain word starts and where a double word starts here. So we want to make sure that we're not overlapping of bits, right? So if we have something that's making use of IW.2, but we also have %ID0 in our program, well then these two, this word and this double word, are going to overlap these 16 bits here, right? So we really have to be careful of the overlap of bits and that we don't overwrite another instruction's values with another address there. Okay, when you're looking at your TIA, you can actually like scroll over certain things. So if it's a black line, that just basically means that it's a Boolean value, right? So this input here for this counter, if we hovered over it, it would say that the input is a Boolean value. So each of the instructions within a counter or a timer or anything, you can hover over the line that corresponds to that parameter, and then it should come up in yellow and tell you exactly what type of data types are available for that input or output or preset value or or reset value. Any of these guys will show you the instruction data type. So for this guy, for the count up, the input is going to be a Boolean value. And you'll see that it's black. Anything black is going to be a Boolean value. Okay, if we have a yellow value, then that value can be any number of different data types, right? So in this case, it's saying that the preset value can be an integer or a word. Okay, so if you hover over a yellow value, it should provide you with the different types of data types available for that specific variable, right? If we look here for the current value, again, it's going to be either an integer or a word to hold those values, right? And you can see here that, like an example here, we have a Boolean value of %m0.0. This start push button is just going to have a value of 0 or 1. Whereas this counter CV value, it can have a value, up to 32,767. So we need to have a value of a word, right? So we have %MW4, and that word will hold that integer value for the current value of the counter. Okay, so anything black is basically a Boolean value. Anything yellow can be any number of different data types, depending on the instruction that you're looking at. Okay, so obviously a bit is just a 0 or a 1, right? So when you have a Boolean value, it's basically a 0 or 1, false or true, voltage or no voltage, right? And the voltage that we're usually working with would be 24 volts or 0 volts. So a Boolean value is just basically on or off, or a 1 or a 0. So there's only two instances that this can take place. It can either be a 0 or it can be a 1, and that's all that a Boolean value can hold. So if you try to put an integer value into a Boolean value, then it'll tell you that there's a data type error. Okay, examples of Boolean values what we've seen throughout the course would be %i0.0, %q0.0, and %m0.0, right? Or m0.1, m0.4, m0.6. Each of those are specific Boolean values, right? So we saw that with bool in that we have a start push button. This guy has a status of being pressed or not pressed, right? A 0 or a 1. And then this output right here, %q0.0, it only has two states. It only has an on or an off state. Okay, so I'm sure everybody's clear with the Boolean example. So let's move on to the byte. So the byte, I'm just going to scroll out here. The byte is 8 bits, right? And that's what makes up each of the next subsequent data types. So everything's made up in terms of how many 8 bits are within there. Okay, so 8 bits make up a byte. Each bit in the byte has its own position and its own specific address, right? So, this might be M0.0, M0.1, M0.2, M0.3, and the combination of from M0.0 to M0.7 creates 1 byte of information. Okay, the address for these guys, if you're going to use a byte, would be %MB, right? Or that's for a memory bit, or IB, right? Or QB, right? But most of the time, if you're going to make use of just a byte, it would just be a %MB. Okay, again, this one here, if we're looking at the byte, the least significant bit would be the rightmost bit, right? So this one right here is the same as if we had just a bool, right? So this has the least significant bit, and then the most significant bit would be obviously over here, right? That's the largest value out of that byte there. Okay, there's also, as we go through, we're going to find that there's signed values and unsigned values. If you have a signed value, then you basically get half of the output of that specific amount of bits, or in this case, byte, right? So a signed integer, or what's called a short integer, will have a negative and a positive value. And so the negative value would be negative 128, and that would go up to 127. Okay, positive 127. Why is it positive 127? Remember that we start at 0, right? So 0 is a placement within that byte. So it goes from 0 to 127, and then -1 to -128. Okay, an unsigned integer is going to have 256 places, right? There are 8 bits. Each bit has the ability to either be a 0 or a 1, right? Because we're talking about binary values. And so if we go 2 to the power of 8, that's going to give us 256 different variations that are available with an unsigned integer. Again, there's 256 variations here with a signed integer, but again, it only goes to 127 because we've made use of the positive and the negative. If you're just using positive values, then you can get 256 different combinations out of here. again, the number is going to be from 0 to 255 because we're starting at 0. So everything in terms of Siemens PLCs are based on these bytes, right, which are basically 8 bits, right? A word is going to be made up of 2 bytes, and a double word is going to be made up of 1, 2, 3, 4 bytes of information. Okay, signed integers, right? We just mentioned this. They're going to be 8 bits or 1 byte, right? The name, there's 2 different names that they use for this. It's either a short integer or a signed integer, right? So in this case, we can go from minus 128 to what we said to a positive 127. So with this one, we've got bits 0 through 7. But if this is a signed integer, then the last bit right here doesn't hold the value. It holds the sign. So for all of these guys, whether we're talking about, a byte or a word or a double word or something, if we're doing a signed value, then the last bit is going to be holding the sign. For all of those guys, a 0 is going to be the positive value. And if we have a 1 in this particular bit, that's going to be a negative value. Okay, so in this case, if we have a 0 here, then our value is going to be a positive value. So here we have positive 54. So the binary 0, 1, 1, 0, 1, 1, 0, that provides us with the value of 54. This bit right here would be 2 to the power of 1, so that's 2. 2 to the power of 2 for bit 2 would be 4. Bit 4 would be 2 to the power of 4, giving us 16. And then bit 5 is going to be 2 to the power of 5, giving us 32. 32 plus 16 plus 4 plus 2 gives us a value of 54. So we can take any integer value and then describe it with a binary value, right? And the size of that binary byte is like the maximum size is dependent on the maximum number of bits that we can make use of, right? So in this case, the maximum we can have is positive 127. So a signed integer or a shorter integer would be fine for storing like smaller values of integer values, right? Integer values being whole numbers, right? Not decimal places whatsoever. So in this case, this is an example of a short integer example. So if you want, you can take, just open up your TIA, open up your base PLC program, drop in an add instruction, and then I've got 2 values coming in here, right? So these are 2 bytes, %MB0 and %MB1. I've just named the value A and value B. So if I'm adding these guys up and I have a short integer that's been used or a signed integer, then obviously the addition of 17 and 5 gives me a value of 22, right? Well within the maximum of the 127 there, okay? Again, different values for each of these inputs and the output, right? M byte 0, M byte 1, and M byte 2 for the addition result here. Okay, because this is a signed integer, I can have a negative value. So in this case, for my first input, I've got negative 32. Second input, I got negative 67. And the combination of those guys is negative 99. Okay, so if you're using values that are positive or negative, you can make use of the signed values. Okay, obviously the maximum is 127, right? So in this case, I've got MB0 being my input, right? And I'm trying to change that to 127. MB1 is a value of 1. So the maximum is 127 if I'm going in the positive direction. So if I try to take 127 and add 1, it's going to give me an error. It says the entered modified value exceeds the range limits of the data type. Okay, so be careful with these guys. And if you're moving memory, bits or bytes or words around within your program, just make sure that you're keeping track of the size of the data that you need and that the specific byte or word or double word that you're using has enough placements in order to move that specific value. If I wanted to move a value of 128, I cannot make use of this signed integer, right? Because the maximum is 127. Okay, so try this out, see how it works, and you'll see that the maximum is 127 for this signed or what they call a short integer. Okay, if we have an unsigned integer, then again, that's going to be 8 bits or 1 byte. Okay, they only consist of the numerical value. It's not going to have a sign. So now bit 7 actually has a value. right? That would be 2 to the power of 7, giving us 128. For this binary value, I've given a value of 1, 0, 1, 1, 0, 1, 1, 0. And remember that each of these bits corresponds to a specific power of 2, right? So this is 2 to the power of 1, 2 to the power of 2, 2 to the power of 4, 2 to the power of 5, and then 2 to the power of 7. So for this guy, we got 2 to the power of 1 giving us 2, 2 to the power of 2 giving us 4, 2 to the power of 4 giving us 16, 2 to the 5 giving us 32, and 2 to the 7 now, instead of being a sign, it's an actual value of 128. When we add all these guys up, we got 128 plus 32 plus 16 plus 4 plus 2, giving us a positive value of 182. Okay, well within the range of the 256 or 0 to 255 that we can get with an unsigned short integer. Okay, an example of that is seen below. Again, same add instruction here. Right, so here I've changed the data type to an unsigned integer here. So now when I add the 50 and the 25, obviously I get 75. Okay, so same instructions we had before, MB0, MB1, and MB2, same sizes, right? But now we've used an unsigned integer, and by using an unsigned integer, we're now being able to go from 0 to 255. Okay, this next example here is again outside of the range of that specific data type for the unsigned integer, because I'm trying to, so disregard the 50, right? This was my previous value. I had 50 plus 1, give me 51. Totally cool with this data type. But if I try to move a value of 255 and then add 1, then that's going to try and get 256, right? So 256 is outside of the range of the unsigned integer here, right? Maximum would be 255. So you're seeing that if you're going to use values that are larger than 255, you're going to have to use more than a byte of information, right? So most of the time we're using words or double words within our PLC programs, or integers versus double integers. Okay, same example here. If you try the same with decimal format, so here what was I using? I was using hex here. So here if I use the decimal format, then you'll see that when I tried to put that value of 255 in, by changing the format that I'm trying to modify the value to, then it has an overflow, right? So remember that 255 plus 1 is 1 above the maximum value for the unsigned integer. So here you can see that it rolls over, and all of a sudden we have a -1 going in for MB0, and then it gives us the wrong addition results. So this is something to think of when we're looking at the next instruction with the math instructions. If you don't use the right size of data type, then you're definitely going to get errors as you try to manipulate the data there with addition, subtraction, multiplication, division instructions. So always keep track of the data types and make sure, again, that we're not having an overlap on the bytes that we're using there. Okay, next ones are integers. So these guys are the ones that we're going to be using the most within our PLC programming, right? So, and again, we have signed and unsigned values. Okay, so in this case, a signed integer is going to have 16 bits, or 1 word here. Okay, or in that example, 1 word would be 2 bytes of information, right? If we have 16 bits, that's 2 groups of 8, so that's obviously 2 bytes of information. Okay, the minimum is going to be negative 32,768, and the maximum is going to be 32,767. Okay, we're starting at 0, so again, the positive value is always going to be 1 less than the negative value. Okay, an example of an integer would be %MW0, right? Or %IW0, or %QW0, right? The W is showing that it's a word of values. Okay, so they're great. You're going to use the integers the most within your programming. And everything that I'm showing you from this point to the real values are going to be different integer values, just with different numbers of bits within them. Okay, so an integer is a great choice for encoder counts, total events and production cycle, steps of a sequence, timers and counter presets, math operations, analog inputs and outputs. Right, so they're the ones that you're going to use the most. Okay, in this case, we have a signed integer here. So the last value here, if it's a 1, it's going to be a negative value. So if this case, if we have 16 bits, 0 through 15, and I've chosen 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0. Each of those guys has a specific 2 to the power value, and the addition of all of these values that have a 1 in their place, right? 2 to the 10, 2 to the 12, 2 to the 7, all of those guys would add up to 18,762. Again, well within the range of our negative 32,768 max. Right, so we said that they're part of counters. So if you open up your counter and you look at the different data types for each of the different variables there, you can see that the count up and the count down are both Boolean values. Okay, the reset is going to be a Boolean value, but stuff like the preset value and the current value are obviously going to have values greater than 1, right? So they're going to have values that are already set. So these are already preset to be an integer. So the preset value and the current value are both integers. Okay, if we're going to make use of an unsigned integer, again, most of the time you'll be making use of just an integer value, but if you wanted to maximize that guy, then you would use an unsigned integer. Again, 16 bits or 1 word doesn't change the size of the amount of bits that are there. It just changes this bit right here. Bit number 15 is no longer a signed value. Right, so now that we put the same values as we had before, right, so the equivalent value of this guy with a sign is negative 18,762. If we have the same number of bits, but this is no longer a signed value, it's a value of 2 to the 15, now that same binary value becomes 46,774. Okay, so signed values are obviously going to have less data, but you get the ability to do positive and negative values. Unsigned values are going to have more data available in the positive direction. Okay, again, same addresses. We're seeing that MW0 is an example of a standard signed integer, and MW0 is also a standard variable for an unsigned integer. It doesn't change the size of the amount of bits that are available. It's still a word that's being used. A word is going to be obviously 16 bits. Or 2 bytes, right? So here we said that an integer is 16 bits, whereas a word is also 16 bits, right? So there's really no difference between a word and an integer. They both have 16 bits of information. Okay. The only difference is that a word has only unsigned values. Okay. So if you're going to use signed values, being positive or negative, then you should address them as an integer. Okay, or take the data type and change it as an integer, right? Sorry, same address. It's still MW0. Okay, but if you're using a word, it does not have positive or negative values. It only has positive values. So in this case, the maximum that we would have would be 0 to 65,535, right? And this should be a 16, right? Because there's 2 to the power of 16. Okay, so moving on from the word, which is again 2 bytes or 16 bits, right? So an example there would be the value for the CV, right? We're probably, if we're going to move this somewhere else, right? So in this case, we have a bottle detector that goes into an up counter. The up counter data type is an integer, and we saw that it was an integer because for those counters, right, we can see that the current value is set as an integer. So in order to move that current value to a different place in our program, or to use it and then use a comparator statement, right? Here we have an equal sign here. Then in this case, and this should be 48 here for the second box of beer, but if we're taking this and moving it over here and using an equals sign, 24 counts is going to equal our first box of beer, right? So here we have a word value. To take that value of 24, move it over here, see if it equals a standard constant value of 24, and if it does, then have this output Q0.1 light turn on. Okay, obviously this one should be 48. Made a mistake here, I'll have to amend this. But that same word is being brought down here, and when compared to 48, if those two are true and it's equal, then we're going to get our second box of beer out. Okay, obviously that value of 48 is well within our maximum range of 65,535. Okay, so the maximum That's another thing to think of, is that the maximum that your current value can have, if the data type is an integer, well, the maximum is going to be 32,767, right? Okay. Then if we're going to use even more information, then we're going to, or bits of information, then we're going to make use of a double word. Okay. So a double word is now 32 bits, which is 2 words or 4 bytes. Okay. Again, each bit in the double word retains its own position and specific address, right? And so in this case, we're going from bit 0 all the way up to bit 31. So a double word is going to have a disgusting amount of information that it can hold, right? In this case, it's 2 to the power of 32. So there's, what is there? 4,294,967,296 different numbers or combinations that are available there. So a double word will easily take any of the information that you're moving back and forth within the PLC. Okay, there are values that are larger than this, but a double word is basically the maximum that we're going to see in this course here. Okay, so in this case, if I look at %MD0, so double word 0, that's a double word, right? So that means that it contains both MW0 and MW2, right? So it's going to keep the word 0 and the word 2. So be careful that you don't use these ones. If you're using MD0, don't make use of the word 0 or word 2, because this MD0 already contains all of those values. Or it contains the 4 bytes, right? It contains MB0, MB1, MB2, and MB3. So when you use this double word, you have to keep track of the fact that all of these guys are already being used in order to make up this double word of information here. Okay? If you're making use of MD0 and then you're going to use another double word afterwards, and this is the issue that I had for quite a while. I kept screwing this up over and over and over. A double word, when you go to the next double word, it's 4, right? So you have to add 4 here. So it's, first one was MD0. Then your next double word is going to be MD4. Then your next double word is going to be MD8. Next double word is going to be MD12. Okay, so it goes up by 4, and that way it keeps track of the 4 different bytes. If you try to use MD0 and then MD2, then again, you're going to have overlaps between those 2 double words, and then it's going to screw up your program. Okay, an example of where you'd have a double word is where we're taking a raw integer value, right? So we're taking a value of 0 to 27,648. So we're going to talk about this in the next subsequent videos when we look at analog inputs being current or voltage. With the Siemens product, it doesn't actually go to 0 to 32,767. So it goes to a maximum of 27,648. And in this case, we have a norm x, a normalize, and a scale x. We're going to go into this in a little bit more detail. But in order to have this raw analog value, 4 to 20 milliamps coming in, and then having a scaled analog value, MD104, right? So that we have a double word there as our output. We have to make use of both a norm x and a scale x instruction. In order to take the value from one instruction to the next, then we just have a buffer value, right? So in this case, we're actually going from an integer value as an input to a real value. We'll talk about real value in a couple of seconds. And then that real value goes into the scale x, and we have a real value as an output here. So here, if we want to have all this information from 0 to 27,648, and we want to make use of all the decimal places there, we're going to make use of a double word to hold all those values. Okay, we need to have a range that accommodates that large number of values. So in this case, if we're going from 0 to 27,648, then we're going to have to make use of most likely a double word to hold the values. Okay, other examples would be double integers. Okay, so double integers again can have a sign, right? So be minus 2,147,483,648 to positive 2,147,483,647. Okay, So another thing here you're seeing is that double word and double integer both have the same addresses, right? So if we're using MD0, then that MD0 can be both can be used for either a double word or a double integer. Okay, in this case, if it's a double integer, it's still whole numbers, right? We're not talking about decimal places yet. We're just talking about larger whole numbers. And if you're using those massive amounts of data, then you're going to have to use of either a double integer or a double word. Okay, again, with this guy, if we're using %MD0, then the next available double integer address would be MD2. Okay, MD0 is going to contain the first word, MW0, and MW1. Okay, so here we saw with the same example, we had values coming in with the norm x to the scale x. And in this case, I want to send a value out to my analog output, %QW96. So in this case, I'm going to make use of the double integer there. Okay, again, unsigned double integers, that just means that we don't have a sign. And so our maximum value is going to be 4,294,967,295. Okay, finally our last one. So everything we've shown up to this point were integers with whole numbers. But if you're going to make use of something where it has a decimal place, that's where you're going to make use of a real value. So in this case, if you don't have to use a real value, don't use a real value. Okay, a real value then has decimal places, and if you're going to use whole numbers and you end up using a real value, then you may get some swaying of your data because of that decimal place, right? It may round certain values. So if you don't need to use decimal places, then always use an integer or a double integer. Okay, but if we're making use of decimal places, then we're going to have to make use of a real or a floating point value. Real value is 32 bits, 2 words, and obviously 2 words or 4 bytes are information. Okay, your range is massive for these guys, right? So it easily holds a disgusting amount of information. And again, if you're using a real value, then it's going to have 32 bits or 2 words. Okay, so again, if you're using addresses, then you'd have to make use of a double word, right? %MD0 would hold the 32 bits, but remember that you're using 4 bytes, right? So your next address, if your first address was MD0, your next address has to be MD4. Next address would have to be MD8 and then MD12. That way we're not having any overlap of the bits between different addresses there. Okay, so real or floating point values are going to be able to make use of decimal places. So in this case, if I'm looking at a value from 0.0 to 27,648.0, and I want to have all the nuances or all the decimal places between them, then I'm going to make use of the real value to transfer it over. And then finally, I'm going to change that real value to a double integer to output to %QW96. Okay. Within your PLC, there's a couple places where you can see more information on these data types. So if you want to see what's called your assignment list, it's very cool. It's a table that shows you all of the addresses that you're making use of in your program. And then it shows you whether there's basically an overlap between those data types. Okay, so with this case, you right click on your PLC, you scroll down to the bottom to assignment list and click on assignment list, and then it'll show you a graphical representation of all of the bits and bytes and words and double words that you're making use of in your program. In this case, I believe it has to be part of your OB. You have to have actually made use of that address. You can't just have it in your PLC tags. It has to be made use of within the program here. So in this case, we've got a certain bit that's being made use of here in %IB0. We have a word of output, so if we're making use of %IW64, then that IW64 is making use of 2 bytes of information here. So it's awesome in that it gives you a graphical representation of the different bits, bytes, words, and double words that you're making use of. And then you can see whether if you've made a mistake and you've overlapped some information within your PLC program. So here we can see that I've got %m0.0 that's being made use of right here. Okay, because I've made use of that, then this byte is basically not able to be made use of. So if I want to make use of a byte later on in my program, then I'm going to use %MB1, okay, or MB2 or MB3. If I'm making use of a word, if I'm using %MW4, then %MW4 is making use of 2 bytes of information, MB4 and MB5. Okay, if I'm making use of %MD6, so double word 6, that means that I'm making use of the first word value right here, right? So 4 bytes are used here, and another 4 bytes are used over here. Okay, so keeping track of your addresses is easier if you take a look at the assignment list. And again, to get to the assignment list, you're right-clicking on the PLC over in the in your project tree, and then going down to the assignment list to access this guy. If you want more information on each of the different data types, then if you go to your tag table, so here I'm in my PLC tag table, right? Obviously all the values here are bool, but it will tell you the specific type of data type that you've used for each of your different addresses there. Okay, if you click on there, then you can click on overview of the valid data types. Okay, or again, you can go F1, and that brings us into our information system. And then within the information system, it's got all the information, obviously, that you need, right? So, some of the stuff that I put into the textbook really wasn't needed, because everything that you need to know about TIA is available within the information system. So in this case, you're hitting F1, or you're going to your tag table, clicking on here, and then going to the overview of the valid data types. And there it's going to give you all the information you need on the valid data types, binary numbers, integers, floating points, right? All of these guys will be available. So it tells you, then it also tells you specific data types that are available for certain PLCs. So it'll show you which one's available for the S200, the S300, the S7-1200, and then the S7-1500. So not every PLC is going to have the same data types, right? As you move up from the 300 to the 1200 to the 1500, then obviously you're getting more and more expensive and larger in the PLC. So you're going to have more data types that are available here. So hit F1, and then you'll be able to get all the information that you need from the information system within TIA. Okay, I tried to summarize everything here, guys. So if you were just wondering on the sizes of each of the different values, basically what we're going to be making use of would be Boolean values for on and off, integer values, right, going from 0 to 32,767, word values, and then the last three we would be using would be double integers, being 32 bits, double words being 32 bits, and then if we need to make use of a decimal place, then we're going to be making use of a real or floating point number. So you can always go back to this chart, which at the moment is on page 344, and then you'll be able to access all the different data types, see what type of address is there, and then see your maximum numbers that are available for each different data type. All right, guys, hopefully this helps, and to show you different sizes of data types. Let's go back up to one last thing that we'll finish off with. Okay, so I find this page to be the most helpful in that it shows us specifically where your bits are, where a byte would be found, how many bytes make up a word, how many words make up a double word, and then this one helps me to visualize exactly where each of the addresses are going to be sitting, right? So if I'm going to make use of like %ID0, I know that it makes use of %IW0 and %IW2. Okay, so if I'm using a double word, then my next address, like we said numerous times already, has to be %ID4, right? That way I'm not overlapping bits from one instruction to the next there. So I would reference this diagram here to show you the difference between integers, double integers, real values, words, bytes, and bits. All right, guys, I'll leave it there. I'll see you guys on the next video. I believe the next video is on math instructions. All right, guys, thanks for your patience. See you in a bit.